And how do I put this in screen? All right. So recording today's lecture, please try. Brett won't be here today, so I will be multitasking, and I'll be probably be able to look at Discord on my phone, but post everything that only your questions unquestioned during lecture. So I'll try to keep an eye. If I didn't see a question and you think it's important, just let me know if you're also on Discord. So, all right. Before that, the passcode to the exam is going to be to the practice exam. All right. So on Monday, I covered first order system. We did a couple of examples, and hopefully everyone has an idea what the first order system is. And if you see a plot, you're able to write the transfer function and the other way around. Now, we will do the same thing for second order system. And as far as system, they are going to be either first order or second order for us, at least in this course. There might be multiple system, but that's the max order is going to be 2. So that will be good for us. And if it's not 2, we will make it 2, right? We put in a status representation and then decrease the order to 2. Usually they look like this: y double dot of t, that tells us the order, plus some coefficient multiplied by y dot of t, and some coefficient multiplied by y of t, could be some coefficient multiplied by input. Now, if we look at the base format, basic form, which this is the basic form, the coefficient of y dot and y have a specific meaning. All right, so we want to put them in this specific format. Now, if we have this format, g of s, which is ys over us, your output over input, your output here is that y of t, right? The state that you're trying to find, over your input, which is u of t, and in Laplace is u of s, is going to be, someone just left. There's one more password. It's okay. If you don't want to learn, I cannot push you. All right, so y of s over u of s is in the standard form. In the numerator, you're going to have omega n squared, okay, divided by s squared, because it's second order, plus 2 zeta omega n s. So there is an s here, plus omega n squared. So this is the standard form. We can rearrange the denominator to make it look like s plus sigma square plus omega d square. I will define what omega d and omega n are, but you can always rearrange your denominator if you're in basic form to get here. You remember the definition of S domain, when we had S, we wanted to relate it to frequency domain. How do we define S?
It's the, I think sigma
plus j omega. So sigma was the effect of if you had decay, right, or growth, e to the power of something, and j omega is frequency, sine cosine wave, right? So your S domain is combination of these two, if you remember that discussion. So here, this sigma is basically this sigma, and then omega d is slightly different from there, but it still is a frequency. So if we are in this basic form, our omega n is our undamped natural frequency. So omega n comes from the system itself. It's the natural frequency of your system. Zeta is your damping ratio. You have heard about damping ratio before. It's the same thing. The damping ratio of your system. And sigma is the real part of the pole we just saw, right? And omega d becomes the imaginary part of your pole. So if I can put in basic form, I can actually get the poles of my system from here, the real part and imaginary part of them. All right. And also you can always put the denominator equal to 0 and find it. These are the same thing. The good thing is when you have basic form, you can just by observation kind of calculate where your poles are. Now, one thing to add, I think is not in my annotated lecture here, your DC gain is 1. So if we had a DC gain of more than 1, then it will be added to our basic form. All right, so the default is K is equal to 1. It's not written, so that's like 1 times omega n squared. Good. So you want to keep the basic form, how it looks like when you are dealing with second order system. If your system is not in basic form, you'll put it in basic form. If you have the basic form, you can find all of those information, correct? You just put them equal and then compare 1 to 1 and find those values. We actually evaluate our second order system on this basic fundamental, comparing one to the other. Now, before we get there, if you want to find the poles from the denominator, if you calculate, you get your poles to be this expression. So negative sigma, zeta, which is your damping ratio, I think we call this zeta, times omega n natural frequency plus minus omega n times the square root of zeta square minus 1. All right, so that's going to be the formula for your poles. It's good to keep it around because you don't have to calculate it again. Now, we can find system response based on the poles and the behavior of our system based on how this expression is behaving. If your zeta is equal to 0, let's put this here. If zeta is 0, what will be my poles? I'm going to show poles by S. What will be the value of the poles? Right? This is the equation for poles. So I'm gonna check for different values and see what happens. So damping frequency has an impact on the behavior of my system. All right. That's why I'm saying that I'm gonna put zeta equal to 0. I'm starting from 0 and want to see different cases. If zeta is 0, then poles are imaginary plus minus j omega n. Right? Then I also have this zeta 0, I forgot that one. So actually this is here. So we have 2 zetas, both of them are zeros, then negative under the square root, so that's imaginary number. So you have negative j omega n plus minus. So you're gonna have 2 poles, both are imaginary, right? So these are valuable information. So think about, all we have is a transfer function of our system. By looking at the transfer function, the denominator, right? If I know what zeta is, I can tell how many poles my system has, what kind of poles they are, and how the system behaves. You can actually estimate the plots, how they look like based on this information. So this is a very important slide. Important. In what sense? Exam, homework, I don't care. In sense of, do you understand control? How can you design a controller? So it starts from here, all right? Now, the other case, so we are gonna play with this zeta. So zeta can be 0, 1, greater than 1, smaller than 1. This is the 4 cases we're gonna check. So we check 0. Now, if zeta is less than 1, what happens under this square root? Zeta is less than 1, but it's still a number. Are we going to have a negative number or positive number? Negative, right? So that is square root, we can take a negative out. So we will see an imaginary components, right? That's the point. So then this is also non-zero. So we're going to keep that there. So S becomes negative sigma zeta omega n plus minus, because this is non-zero, it's just less than 1. And then since zeta is less than 1, we know we're going to have an imaginary pole, j, and what's the value? This. So if you calculated your damping ratio and it's less than 1, you know that you're going to have 2 complex poles. All right, I haven't talked about the red stuff that I wrote. I'm just going through the poles. Once we are done with that, we're gonna go check yes.
Wouldn't it not factor J pulled out of the square root?
No, so let's say if we use what zeta is, I would say like 0.5. So I said 0.5 minus 1 is negative 5.5. Then I take the negative out, say it's j. But since I don't know what it is, I'm leaving as it is, but I'm saying that it's going to be imaginary. Now, even if you take that one negative out, it will be 1 minus zeta 2. This is negative positive. But I'm not doing that right now. I'm just telling you that this pose is going to have imaginary component. Then once you know what that is, you can write the correct answer. All right. We will see that when we are dealing with this case, we will actually write 1 minus 6 as zeta squared to kind of make it correct. Yes.
J for zeta at the very beginning of the equation.
So compare it to this. What do you think? It is zeta. Yeah. Your handwriting is worse than mine. So.
Oh, I'm sure.
Okay then.
I don't have to cheat people.
You have to what?
I said I don't have
I'm not teaching you.
to.
Try to write better, but that's all I can do. The distinction is the dot on top, right? All right. So if zeta is equal to 1, what's going to happen? Like following this static procedure, looking at our equation, what would be the poles? James, this James. Negative, and zeta is 1, right? So zeta omega n, which is negative omega n, right? You can either keep the zeta there, but we already know it's 1. But I'm going to keep it just to show which case is going to be. Then our last case is when zeta is greater than 1. So under the square root is going to be a positive number. So we don't have any imaginary part. Just going to be a ugly number, but whatever. Then we have a real part, which is this part, right? So we're going to have 2 real poles. And going to be 2 distinct real poles because we have negative zeta omega n plus and minus zeta squared minus 1. So Michael, that's why I kept it like that. So you can see, depending on the value of your damping ratio, you could have different combination of poles. Now, starting from top, if your zeta is equal to 0, you're going to have 2 pure imaginary poles. It means that it exists. It's not imaginary. It's on imaginary axis. It's only going to be on imaginary axis. So only have imaginary component.
That's what the question is going to.
What happened? Oh, I missed the omega n. Yes. I was so excited to see. That's what happens. I get excited. There, I'll put a tail here so you know what this is. Great. All right. So, case number 1, zeta damping ratio is 0. What does it mean? The system never gonna be damped, right? So it only stays in sinusoidal. So only we have pole on imaginary axis. So as expected, we will call that system undamped because it's not damped. There's no damping ratio. If the damping ratio is less than 1, we saw that we are going to have complex poles. We call this system underdamped. It is important if you remember damp, underdamped, overdamped for each of these categories. Okay. So zeta less than 0, underdamped. Zeta equal to 1 is critically damped. And we are going to have repeated real poles. So it's going to be real pole values. If zeta is greater than 1, guess what? Overdamped, right? So if you think 1 is the line that you're thinking, below 1 underdamped, over 1 overdamped, add 1 critically damped, and if it's 0, there's no damping, so it's undamped. Make sense? Should be easy to remember. So find a way of remembering this. So for me, 1 is the line, critically damped. So if zeta is above 1, greater than 1, my system is overdamped. Yes. What do you mean systems that are not physically real? Yeah, whatever is damping, it doesn't matter. If you can put a system equation in second order, whatever is the coefficient of your y dot or whatever dot, that has damping ratio in it. So you can define damping ratio in any system. You'll see, I'll show you the response, okay? That will probably hopefully help. So now we have 4 cases, right? So a second order differential equation can only have one of these 4 shapes in the response. Doesn't matter what system it is. You just sub between the mechanical and electrical, they're analogous, right? You can go from one to other. Now, damping will have different interpretation in different systems, but it acts the same. So if you have an underdamped system, when zeta is less than 1, okay, is not 0 though, is non-zero. So here is just to show that is not 0. You're gonna have 2 distinct poles, and your response always gonna look like that, the first one. If we have a critically damped, we are gonna have 1 or 2 repeated poles, and then this is how the system response would be. So if you draw a step of that system, it will give you that. So you, by looking at transfer function, we can draw or at least expect how our response would look like. How cool is that? Like magic, right? Or at least that's how I think. If it's overdamped, you're gonna have 2 distinct real poles. The shape will be the same, but if you draw, so we will see the difference between them. One of them will never reach the steady state that we expect because it's damped too much. If the system is not damped, it's sinusoidal, is this 4th case. So you see that the poles are on the imaginary axes, nothing will damp the system. If you remember from what lecture was, very beginning, when I was discussing a second order system, I said that we could have an exponential element, right? Okay, butter your fingers. E to the power sigma t plus a sinusoidal, which is the effect of our frequency, right? Now, if you put these together, so this is the envelope, and then this is your sinusoidal. So that's that damping effect that we are discussing. So this system is being damped. This system is being damped. Now, these 2 cases, they are damped too much, or critically damped is just enough damped. Overdamped is just damped too much. That's not what we want usually, all right? But they look the same kind of. The difference is we have to read what value we wanted to reach out, and you'll see that for overdamped is usually way below what you wanted. And this one doesn't have that envelope, so it's not damped at all. So from this transfer function, I can predict the shape of my response, which is, if you're in math class, plot the, I don't know, the solution to this equation. That would be the case, all right? So the solution to this equation, or this equation, basically, that is the solution to that equation. We put it in transfer function, and then we can find those critical values, and we can actually plot it. You don't even need your software to do that. Today we'll do it by hand, the same as we did for first order, right? So there are some points that we need to have to be able to plot. Those are the characteristics of our system. In first order system, what were the characteristics of your system? Which numbers did you need to be able to plot? Do you remember? That appeared also in your basic form. Do you remember? K and tau, basically, and then everything else we just have equation and we can use, right? So here we just have more of them, but same process. Sounds good? So we're going to use this knowledge we learn and do a couple of examples. So things that you need to have handy is probably this slide. All right. So do you remember whenever we talked about system, we end up saying that, oh, we need to know where the poles are. And then the next question is, okay, why do we care about the location of the poles? Why do we care about it? Because someone told us that if you know where the poles are, you can tell if the system is stable or not stable, it's controlled properly or need to be more controlled, right? So you design your controller based on the behavior of the system that can be predicted from the poles. Now, for second order system, for this example, we are going to see how the location of the pole can impact the response of the system. All right. So I'm going to use one of these examples, one of these four cases. Usually this here with the flower, this is the case that has the most, is the most complicated. It has everything, right? We are gonna always, like, you will see that I always use this case as an example, because if we know this complicated example, we know everything else. Like we can solve for all the other cases. All right. So, my example would be that I will use is going to be under dam system. Which has two complex poles. So if I know it's under dam, I know that it has two complex poles. Now, the equation for the poles S is negative zeta with the tail omega n plus minus j omega n. Now I'm gonna take that, write it properly. 1 minus zeta. So here I factor out that -1 that we were discussing. It doesn't impact because instead of plus, positive, negative, plus, minus behind, you have minus plus behind that here. So you could have negative, positive. Same thing. You still have two poles. Now, if I call the real part sigma, sigma is negative zeta omega n. And I will call this one omega d. This is the imaginary part, right? So I can write not w is omega n 1 negative square root of zeta square. If we plot these two on our S plane, right? So this is my pole, this value is my omega d, and then this value is sigma, which is on the, you see the negative part, so this is negative sigma omega n, right? So on the negative side of it. Now, if we use Pythagorean theory, if I pronounce it correctly, I can find this value. This is our omega n. Omega n square is going to be omega d square. You should be able to do all of this after this slide. Okay, so try to understand what is happening. That's all you need. So this holds. Also, if we call this beta, I can write what is cosine of beta. So I can sigma over omega n is zeta omega n over omega n. So it becomes zeta. All right. So we will define this beta as an angle that the cosine of beta is our damping ratio. Now let's check different cases with beta. If cosine of beta is zeta. If beta is 90 degrees, what will happen? What would be the value of zeta? Zero? Well, cosine of beta is zero, right? So your zeta is going to be zero. It means that this line will be a line here, right? So if you don't have damping ratio, your poles are going to be on the real axis. So this is the same thing as we said before. So if you forgot, this is a very useful visualization of if zeta is equal to zero, where the poles are going to be. So the poles will be on your real axis. If beta is 0 degrees, what will be your zeta? 1. So means that this guy will go here. So your poles will be on the imaginary line, right? You remember if we have zeta equal to 1, we're only going to have imaginary part. So these are the two extreme. I know what you want to say. Let me finish. These are the two extreme. All right. So from these two, from this plot, we can conclude. This is the part that I want you to remember. As the poles get closer to your real axis, your beta decreases and your zeta increases. So to have a bigger damping ratio, where do we want our poles to be? Closer to the real axis or farther from real axis? Your zeta changes between -1 and 1, right? Correct? So, well, it can be more, but this is where we're gonna check. So if we want more damping ratio, more damping in our system, where do we want the pole of the system to be? Michael. Yes. So let's review that again. No, it's the real axis, the other one. All right. So I'm going to draw a blank. And so this is my imaginary and real. So imagine, well, not imagine, this is beta, and you can go all the way up here or here. So think about cosine of beta is zeta, right? So if your beta was 0, what was your zeta? 1, right? So you had the maximum. You will be on the this real axis. So saying it backward, if we wanted more damping, we wanted our pole be closer to our real axis, right? If we want less damping, we want our pole to be closer to imaginary axis. Now, why is this important? You will see the behavior of a system and you think it needs more damping. It means that we're going to design a controller that have a pole in it that is closer to real axis. That's pole placement. That's a technique in controllers. I'm sorry, I yelled. I just meant I want to finish this. Okay, I'll go back to that. If your system needs a little bit more, there'll be less damping because it's over damped, one of the cases, right? You want to design a control that has a pole in it that has less damping, so it's closer to imaginary. What does it mean? we will pick a pole that is here. So this has a greater beta and a less damping. In the other case, we will pick our pole here that has less beta and has higher damping. And it would just change the behavior of your system because these are LTI. We can use convolution and multiply them together, right? So let's say 1 over s plus 1 is on real axis, right? The pole. If we multiply this to our system, could be a controller. We just place the pole at -1 because we wanted to rectify the behavior of our system. Does that make sense? So I'm not expecting you to design a controller, do the pole placement. I want you to understand how location of a pole will impact the behavior of a system. And it is true damping ratio. That's why we will see that most of the time we are just playing with damping ratio. All right. Okay. Now, back to your question, Michael. You're good? Okay. Right. So this is the response of which of those 4 cases? Underdamped, right? Good. It's good to be able to call it. So the differential equations are the same. The solution is the same. It's just those values, this coefficient, right, that define what the response will look like, which those coefficients boil down to omega n and zeta for our case, right? Now, before I solve another example of calculating basically omega n and zeta and plotting, I want to show you a few, I want to give you a few names and terminology on this. This is one of the important plots that you'll see. Do you remember transient response and steady state response? You eventually heard that, right? So in this graph, this part is our steady state, right? Because we reached a response and then it's just gonna follow that flat line or changes slightly really low, like you're happy with whatever it is. We call that a steady state. This other part is called transient part. So most of the characteristic of our system happens in the transient stage. And we are gonna define those, all right? The definitions are on the next page. I've already typed them all out for you, but I'm gonna show it here. So I explain it here, but then you'll see the definition in the next page, all right? Here we see, I marked a couple of them. Well, this image has a couple of them in there. So things that you will see, Y max, MP, YSS. Okay, let's discuss those 3. Y max, as it sounds like, is the maximum value of your system, right? That happens. That there's just one point that's one Y max. That point is important for us. Then you have YSS, Y of a steady state. That is the output, the Y that you actually is desirable for you. You want to reach to that point. All right. So YSS is the steady state value. Y max is the one-time high that happens. You don't like it, but it will happen. It's okay. The difference between these two is the overshoot, right? So we call it MP. Now, we call it maximum overshoot because this is overshoot, this is undershoot, this is overshoot, but one of them is the maximum. So we call the maximum, so the difference between Y max and our steady state maximum overshoot, we show MP. When we calculate percent overshoot, percent MP. And we use that in our designs usually. So those are all the value and important values on the y-axis. Now on the x-axis, we have a couple of other values that are important. TP, TS, TR. So TS is steady state settling time, which if you look at it here, it is the first time that the behavior of your system, the response of your system falls into that 2% line. Do you remember where this 2% line came from? Not 3 decibel. 3 decibel is 0.632. 4 times of our, so in first order system was 4 times of our tau. Here, so we don't have 4 times of tau. It has its own equation, but it's 98% of your steady state. So the first time your system stays in that line of 2%, so it's 90, it reaches 0.98% or 1.02. So above and below, you can say that I'm happy, my system is settled. That's my settling time. A lot of time when you're designing a system, they ask you design a controller that brings the settling time to 0.03 seconds. It means that after that, we're fine, whatever our system, however it behaves. Okay, so it's a performance thing. TP is peak time. It's the first time, well, the time of that peak, Y maximum. Pretty simple. All right. Then you have TR, which is T rise time, the amount that takes for your system to go from 10% of a steady state to 90% of a steady state. So this shows how fast your system is, right? So if your TR is small, so I'm going to show 2 examples. So if this was that 10%, right? And then another system, it takes this much. Which system is faster? System on the left. Well, yes, for you, that's that side, right? So TR here, and if it's TR2, TR1 is less than TR2, this is a faster system. Doesn't necessarily mean a better system. It's faster, usually faster is better. But how fast, that's the $1 million question, all right? So these values, these few definitions are really important, and these are part of the characteristic of our system. So they don't directly appear in the transfer function. We only have omega n and omega and zeta there, right? But we will define all of them based on these 2 values. That's the beauty. So now let's go and check some definition. So I don't have Y max here. I'm going to write it down. So your Y max is YSS plus % overshoot times YSS, and you'll see why. So YSS plus whatever is left. The YSS is state, TP, TR, so FV is final value, which is also your steady state, right? SS value. Don't mix it up with the state of space. This is a steady state, like we settle. All right, so these are the definitions, these are the equations. So this is probably the second most important thing you want to remember or have it handy. So 2% settling time T of S is 4 over sigma. What was sigma? Yes, sigma omega n. You write the, just grab the positive, forget about the negative sign. TR is 1.8 over omega n. We had omega n from transfer function. TP omega pi over omega d, which your omega d was omega n square root of 1 minus zeta square. And % overshoot is this equation, e to the power of negative zeta pi divided by square root of 1 minus zeta square. % overshoot is 100%. You just do the percentage. So just time 100 times 100 and then add percentage sign. Good? All makes sense? So you need this slide plus the other slide about that has all the zeta in it to solve problems for second order system. I solved this example and then you can do class participation. I will extend it to tonight, but you will start here. So if you couldn't finish, you can finish tonight, but it will start here. Okay, so my basic form, so you should be able to actually follow me. TS, let's say that I'm gonna assume I have a K. I don't know what my K is going to be. S squared plus 2 sigma omega n s plus omega n squared. Some of you might have done this before. So we are gonna match. So I start from here because this is the pure omega n. Why don't I start from this? Because this is k omega n and this is 50. I have two variables I don't know what they are. So I'm not gonna start from there. So I'm gonna say omega n squared should be 25. This gives me omega n is 5. Now k omega n squared is 50. That gives me k equal to 2 because omega n squared is 25, right? And then 2 zeta omega n is going to be 6. This gives me, so omega n was 5, 2 times 5 is 10, so zeta is going to be 0.6. So I found all the 3 values that I needed. Now, if you want to plot the response, you need all the TRs, TS, right, TP, and you need the maximum value. Now, we will use these to calculate those values. So to plot, I need TP, TR, and I need also Y max, because if I have those points, I can plot them. TP from the equation from previous page is omega pi divided by omega d. This is going to be about 78 seconds. It's important to put that. TS is going to be 4 or sigma is going to be 133 seconds. MP is negative pi sigma 1 minus sigma square, zeta, sorry, square. This is going to be 0.095. So percent MP is 95%. 9.5%, sorry, not 95, 9.5%. Then your Y max is YSS plus percent MP times YSS. What is your YSS? What's the value of YSS based on things that we have? YSS is your steady state, right? 2, your DC gain, plus 95% times 2 is going to be 2.189. Okay. So these are all the information you needed. Now we can plot. We have Y max 2.189. We have our DC gain K is 2. We have time peak 0.78. So this is 1 point. Then I have my settling time 1.33, which was 2%, right around here somewhere. So I'm going to say somewhere here. So I'm going to draw this. It's going to be something like this, like you don't have to necessarily have it. Make sense? Spend time, and it's good if you like open your class participation as a different example and try to copy what I did. You will have the solution to all of this in annotated version. Try to understand it instead of just writing it.